Okay, hi guys. The first thing I'm going to say is I'm just going to draw your attention to this post-it up here. Next lesson, I'm going to do a brief overview of the course. I will set your homework next lesson and I'll give you your textbooks next lesson. So there's nothing you need for today except for a pen and paper. And I will go through the kind of details of the course and how we're going to approach things when I see you in person later in the week. So I thought for today what I'll do is introduce you to one of the first sort of important concepts we're going to look at in the mechanics course, which is constant acceleration formula. And I thought what I'd do is I'll go through this by defining some things we're going to be seeing a lot and understanding what they are so that we can use them effectively. So the first thing is time. Now, time, which we call T, is really important because if we don't have time, and if time isn't changing, then things won't be moving and things won't be doing things, all right? So we think about almost everything we do with kinematics as being related to time, okay? Something moving relative to time or something happening relative to time. Now, if time isn't involved, then we have a static situation, something isn't moving. And we'll think about that idea later in the course. But for today, time is going to be the kind of basis of everything we look at. So we have time, which we call T, and this is in seconds. That is our unit that we use. Okay, I'll give you all the base units for what we're going to use today, but time is in seconds, and this shouldn't be too sort of breathtaking a thing to show you. Time T in seconds is the basis of what we're looking at. Now, the next thing to think about is something called displacement, which we call S. So, displacement, which we call S, is essentially how far something is from another point. Now, you may think, well, isn't that distance? And what I'm going to do is I'm just going to kind of point out the difference in the two. So let's say I have a line here from sort of between 2 points. And I'm going to call this first point 0, or O, the origin, and I'm going to call this point A. Okay, so I have a point A and I have a point O. Now, if I'm a particle or I'm just an object and I travel in this direction from O towards A, at any point along this line, I am at a distance from where I started. Okay, so I could be 1 meter, 2 meters, 3 meters, 4 meters, etc., etc. Okay, let's say that A is 5 meters from the start. So if I'm at this point here, my displacement from 0 is 1. Okay, so my displacement is 1 meter. If I'm here, it's 2, 3, 4, and 5. Okay, that should be obvious. So what essentially we say is we say that this is a positive direction. Okay, I go 1, 2, 3, 4. I'm going upwards in numbers and it's positive. Let's say that I go this way by 1 meter. Then if I'm in this position here, I must be negative 1 meters displaced from this point. So we have a positive and we have a negative direction. The distance of this point here, I'll put them in a different color for you. The distance of these 2 points away from my 0 is the same. So the distance tells us less than the displacement. The displacement at this point is positive 1. The displacement at this point is negative 1. Positive 1, negative 1. Just think of an axis on a graph, okay? And that should help you. So another way of thinking about this is that displacement, as in how far you are from a point, is instant. Okay, so where you are at a certain point in time is your displacement. Distance, however, is cumulative. as in the distance you've travelled adds up over time. So I'll show you what I mean by this. If I draw a square or a rectangle, like so, and I label my corners, let's go for this point here is 0. This one I'll call A, this one B, and this one C. And I'm going to say that this length here is 4 meters. So to get from O to A, it's 4 meters. From A to B, it's 3 meters. So to get from O to B, you could tell me you have to go along 4 and down 3. So the distance from O to B equals 7. I think it's difficult to argue with that. You go along here and down that way. However, if you are at B, your displacement is not 7. If you're at B, don't let me draw a line here, do you? Okay. So if I draw a kind of dotted line from O to B, we can actually work out what this length is from O to B. It's a simple one. It's a Pythagorean triple. 3, 4, 5. So that distance O to B is 5 meters. Therefore, the displacement of OB is 5. We've got two different distances here. Sorry, we've got two different numbers here. So this one is 5 meters because B is 5 meters from O at this point. However, you've travelled 7 meters to get there. So the distance is cumulative, we add it up, but the displacement is instant. Where am I compared to this? I'm 5 meters away. However, it's taken me 7 meters to get there. Okie dokes. So that is displacement. And remember that displacement we call S. Okay. Right, moving on. Velocity. So our next letter to look at is velocity. Now, when you see velocity, you may well think of speed. Okay, and I can put that in brackets. Velocity and speed are not the same thing. Okay, speed doesn't, there you go, have a direction. Okay, so if I was to say, you know, I'm going to move at 5 meters per second, the question that would follow that is, well, in which direction? Velocity gives us that direction as well. So again, if you think about our 0 point, if I travel at 5 meters per second in the positive direction, or I travel 5 meters per second in the negative direction, these are different velocities. However, the speed is the same. Okay. Now, velocity, which is something you should already know, is change in displacement or change in distance over t. Okay, we know this because at GCSE you would have used that speed is distance over time. However, we now need to use velocity is displacement over time, or change in displacement over time. Okay, now I could, if I wanted to, put change in time as well to make it a bit more mathematically proper. Another way I could say this as well is I could say that if I differentiate my displacement, as in I do d by dt, differentiate with respect to time, of s, that gives me my velocity. So ds by dt is v. Okay, so this basically means velocity is rate of change of displacement. Okay, so for example, let's get my line out again. If I have my 2 points here. I have my 0 point, and I have point A. If I travel 4 meters to get from 0 to A, or O to A, and it takes me 2 seconds to do that, my velocity therefore must be my change in displacement, which is 4, divided by my change in time, which is 2. Therefore my velocity is 2. Now it's 2 what? Well, if we think about what we've done here, we've done distance or displacement divided by time. So that is m meters divided by seconds. So my unit is meters per second. Or I could write this as ms to the minus 1. Okay, you can use both of these units. I prefer this second one because it's a bit more mathematical. Okay, and when you write acceleration, it makes a little bit more sense as well. Okie dokes. So essentially, velocity is how many meters are you traveling and how many seconds have you taken to travel that displacement. Now, when we look at velocity, we look at 2 types of velocity. We have velocity, which is v, which is final velocity. And we have another letter, u, which denotes our initial velocity. Now, the reason we have 2 different velocities is because our velocity can change. And when our velocity changes, we call this acceleration. So if I have initial velocity and a final velocity, that means that when my velocity changes, I need to have another letter which I use. And this is A. And A stands for acceleration. Now, acceleration is the rate of change of velocity. It is not simply the change in velocity. Okay, if you accelerate from 0 to 60 in a car, the change in velocity is 60. However, we want to know how long that takes to do so. And so that is what we call our acceleration. Rate of change of velocity, if we think about it, we could also go a bit further here and call it the rate of change of rate of change of displacement. If we think about it, ds by dt we call v, dv by dt, as in the rate of change of velocity, we call a. So this must mean that a is also equal to if you remember from our differentiation work, acceleration is the second derivative of displacement. Okie dokes. Now, that's one way of thinking about acceleration using calculus, okay, the rate of change or the derivative. We could also think about it a little bit more simply. We can say that acceleration is my change in velocity divided by my change in time. And we can also write, and this is a very important equation, final velocity subtract initial velocity divided by the time taken to change velocity gives us acceleration. Okay, now the unit for acceleration is, if we think about it, it's meters per second per second. Now this basically means it's equivalent to meters per second squared, which is a perfectly acceptable way of writing this, or perhaps better, ms to the minus 2. Essentially, the ms is velocity divided by s gives us the acceleration. Okay, so let's have a look at a little example with this to put it in perspective. So let's get back our track again. Now, you notice I'm using a kind of diagram here a lot. It is a really useful thing to do yourself when you're trying to work out these problems. Okay, if you have a SUVA problem or a kinematics problem to solve, drawing a little diagram really does help out. So we're going to go from 0 to A and then on to B. Now I'm going to say that it's going to take the same time to get from 0 to A as it takes to get from A to B. So it's going to take me 5 seconds to get from 0 to A, and it's going to also take me 5 seconds to get from A to B. Now, when we are at the 0 point, we are 0 meters per second. At A, we are traveling at 2 meters per second. When we get to B, we are traveling at 7 meters per second. So as you can see, our speed or our velocity is increasing. Now we're going to try and find out what the acceleration is in these two parts of the journey, from O to A and then from A to B. Now acceleration, notice I've put a single arrow for velocity. I like to put a double arrow like this for acceleration. It's just a bit of notation which helps you. So let's work out O to A. So the acceleration from O to A, remember the acceleration is change in velocity over change in time, which we use as V minus U over T. So for this one, which I'm going to call A1 equals 2 minus 0 divided by 5. 2 minus 0 divided by 5 simplifies to 2 over 5. So 2/5 is 0.4. Okay, so for this section, we have 0.4. Now have a think about it. Do you think we're going to have a higher acceleration or a lower acceleration? Well, it's the same time, and our velocity is increasing by 5 as opposed to by 2. So I think we should be looking at a higher acceleration. Let's have a look. So A2 V minus U over T. That's going to give me 7 minus 2 over 5, which is 5 over 5, which equals 1. So 1 ms to the minus 2, our acceleration is 1. Now what this literally means is for every second my speed is increasing by 1 meter per second. Okay, so think about that when you think about acceleration. Just try and make sure you understand the idea behind it. Okay, last thing to look at is average velocity. Now this is a slightly misunderstood idea, and I'll show you why. So let's say we have a journey A to B. We start here, A, and we get to B. Now if you think about it, say we're going from place to place. Say I'm travelling from Ottery to Exeter. It doesn't work in a straight line unless somehow you're flying a helicopter or something like that. We don't go in a straight line. So if I have my journey and I might do something like this, notice how for every step of the way my velocity is changing, even if I'm traveling at the same speed, because my direction is changing. So to work out the average velocity is really quite difficult, okay? Because we are not traveling in the same direction along that line, we can't really work it out simply. So in this case, if we're not travelling along the same line and my acceleration is variable, which it must be if my velocity is changing, then all I can use for this is my change of distance, okay, so my displacement divided by how long it's going to take, okay. So in this case, if the acceleration is variable and the velocity is changing, my V average is going to be my change in displacement divided by my total time. Can we see that makes a little bit of sense? Because I can do whatever I want on this journey, but I'm still going to go the same displacement in a straight line, and I'm still going to take a time. So if I meander around and I take 3 or 4 hours to get there, I'm going to have a lower average velocity than if I go really, really quickly. Okay, you could think about maybe riding a bike to Exeter from Oxford as opposed to driving a car or getting the train. So, if, and this is a big if my acceleration is constant, which by the way we're assuming it is, okay, if we go all the way back up here, constant acceleration formula is what we're looking at. So we're assuming constant acceleration. So if my acceleration is constant and I'm travelling in a straight line, I am, and only in this situation, I'm allowed to use this. I'm allowed to use the idea of mean, okay? So I can use V average equals U plus V all over 2, essentially finding a mean. Okay, so you can imagine if I travel in a straight line, like so. Okay, my acceleration is constant. Then if I start my journey traveling at 10 meters per second, and I finish my journey traveling at 30 meters per second, then I simply do 10 plus 30 divided by 2, which gives me an average velocity of 20 meters per second. Just be really careful with this. This only works if you're traveling in a straight line and if your acceleration is constant. Okay. Right, I'm going to end this video here, and you can have a look at the next one where we'll be looking at how to derive SUVAs.